Hello everyone! In this robotics and control engineering tutorial, we explain how to develop a simple discrete time model of a mobile robot that can be used for the development of algorithms for localization, simultaneous localization and mapping, and dead reckoning. We develop a discrete time kinematics model and we explain several important aspects of this model. The model presented in this video tutorial will be used in our future video tutorials for the development of robotic algorithms. The model developed in this video tutorial is arguably the simplest possible model of a mobile robot. For simplicity and clarity of this tutorial, we focus on a differential drive mobile robot that we introduced in our previous tutorial. A link to that tutorial will be given in the description below. Although simple, the model developed in this tutorial can still be used in practical applications, and the modeling ideas presented in this tutorial can be used as an inspiration to develop models of robots with various configurations. We will use two different modeling approaches. Both approaches will result in the same discrete time model shown over here. The first approach is based on the direct discretization of the continuous time model of the robot kinematics. The second approach uses simple trigonometry and physical intuition to develop the model. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on this YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start with explanations. This figure shows a graphical representation of a differential drive robot that we introduced in our previous tutorial. A link to that tutorial will be given in the description below this video. The robot consists of the robot base with two active or actuated wheels and the third passive caster wheel. The third passive caster wheel provides the stability of the robotic platform, and for simplicity and clarity of this graph, it's not shown over here. Passive over here means that a wheel is not actively actuated. That is, the caster wheel can rotate around two perpendicular axes, however, it's not actuated. Actuated wheels are left wheel and the right wheel. We have two coordinate systems. The coordinate system, capital X and capital Y, is the so-called inertial coordinate system. This is a fixed coordinate system, that is, this coordinate system doesn't move. Then we have the second coordinate system called the body coordinate system. It is the coordinate system with XB and YB axes. The body coordinate system is also called the body frame. This coordinate system is rigidly fixed to the robot body or robot base. Its center is at the point B. Usually the center point B is the center of the mass or the center of the symmetry of the robot body or the robot base. The body coordinate system moves together with the robot. The coordinates x and y are the horizontal and vertical positions of the body coordinate system xb, yb with respect to the inertial coordinate system x and y. The angle theta or theta, however you like to pronounce this Greek letter, is the angle that the body coordinate system makes with the x-axis of the inertial coordinate system. That is, the angle theta is the rotation of the body coordinate system with respect to the inertial coordinate system. The angle theta is called the orientation angle or angular orientation. This angle is also called the bearing angle or simply bearing. Also, this angle is called heading angle or simply heading. Since the body coordinate system is firmly attached to the robot body, the angle theta is the rotation of the robot body. V is the instantaneous velocity of the center of the body frame, and omega is the instantaneous angular velocity of the robot. Next, we need to define what is a robot pose. The robot pose is this vector z over here. It consists of x, y, and theta. The robot pose completely defines the position or location and the orientation of the robot with respect to the fixed inertial frame x and y. From a purely geometrical point of view, the pose defines the location and orientation of the body frame with respect to the inertial frame x and y. The pose is also called the kinematic state. The reason for this will be explained later on in this video tutorial. The precise knowledge of the robot pose is important for a number of reasons. First of all, it determines the precise location and orientation of robot in space. Secondly, the robot pose is used for feedback control. Finally, robot pose information is used in other robotic algorithms such as path planning, obstacle avoidance, and SLAM algorithms. In our previous tutorial, whose link will be given in the description below, we derived a continuous time kinematics model describing the robot motion. The kinematics model is described by these three differential equations. This model connects or relates the instantaneous velocity v and the current orientation angle theta of the robot with the change of the robot pose in the inertial coordinate system. You can see that by analyzing the left-hand side of these differential equations. On the left-hand side, you can see x dot, y dot, and theta dot, and that's precisely the first derivative of the pose vector z defined over here. Next, it's very important to keep in mind that this model is developed by only using kinematics reasoning without taking into account the robot dynamics, that is, without taking into account the mass and forces. In the sequel, we will develop the robot model by discretizing this kinematics model by using the forward-Euler method. Of course, the forward-Euler method is only one among a number of discretization approaches. The main reason for using the forward-Euler method is that this is arguably one of the simplest possible discretization approaches. On the other hand, to achieve a relatively good accuracy of the model obtained by using the forward-Euler method, we need to select a small discretization step. Also, the forward-Euler method might suffer from the stability issues. Some alternative approaches that achieve better modeling accuracy are the trapezoidal discretization method, backward-Euler method, trapezoidal implicit method, and Runge-Kudam method. However, such methods result in mathematically complex models that might significantly increase the computational burden of robotics algorithms. Let's learn how to use the forward-Euler method to discretize the dynamics. Here is our continuous time dynamics, and the main idea of the forward-Euler method is to approximate these derivatives by using finite differences. And here is the approximation. First derivative of x is approximated like this. That is, it is approximated as xk plus 1 minus xk divided by h. Here, h is the discretization step, k is the discrete time instant, and xk is the value of x at the time instant k times h. In the same manner, we approximate the first derivative of y and the first derivative of theta. By substituting these approximations in our continuous time dynamics, we obtain these three equations. Over here, vk is the instantaneous velocity at the discrete time instant k, and omega k is the instantaneous angular velocity at the discrete time instant k. Here, it is implicitly assumed that the instantaneous velocity vk and the angular velocity omega k are constant between the discrete time instants k and k plus 1. From this set of equations, we obtain the discretized kinematics model of the robot given by this set of equations. Next, we need to observe a few important things. First of all, this product, that is, vk multiplying h, is the distance traveled in the direction of the velocity vector vk. Here is the graphical representation. The distance traveled between the time instant k and k plus 1 is actually vk multiplying h, that is the velocity multiplying time, and it is denoted by sk. Next, since omega k is the angular velocity, and it is assumed that angular velocity is constant between the discrete time instant k and k plus 1, the product omega k multiplying h is the rotation angle of the robot body between the discrete time instants k and k plus 1. We denote this angle by delta theta k, and this angle is shown over here. Finally, by combining this set of equations with this notation and this notation, we obtain the final discretized model of the robot kinematics, and here it is. This model is very important since it mathematically describes the change of the pose vector in time. For example, this equation tells us that xk plus 1 is equal to xk plus the travel distance in the direction of the constant velocity multiplying cosine theta k. Similarly, the second equation tells us that yk plus 1 is yk plus sk multiplying sine theta k. And the third equation describes the change of the angle. We derived the model by using the forward Euler discretization method. However, there is a more elegant and more physically intuitive approach for deriving the model. This approach relies only upon simple trigonometry and basic intuition. In the sequel, we explain this new approach. But first, let us analyze the discrete time model obtained by using the forward Euler method. If we ignore the last equation in the system of equations given over here, we are left with these two equations. These equations describe the translation of the robot body along the direction of the instantaneous velocity vector vk, where the orientation angle theta k remains constant. This is graphically illustrated in this figure. We start from here and we go to the end position, where the direction of the movement is simple translation along the direction of the instantaneous velocity vector vk, and vk is constant. We move for the distance of sk. On the other hand, if we ignore these two equations, we are only left with the third equation given over here. This equation actually graphically represents a rotation for the angle of delta theta k. What did we learn from this simple example? Well, we learned that the motion can be decomposed or decoupled into translation and rotation. Well, this is a very well-known fact in kinematics and dynamics of motion of rigid bodies in a plane. Namely, the complex motion of a body in a plane from one pose to another can be decomposed into translation and rotation. And let us use this principle to re-derive the kinematics model by using a more intuitive approach that does not rely upon the model discretization. The idea here is to formally decompose the motion of the robot from the starting point at the discrete time k to the end point at the discrete time instant k plus 1 as follows. From the starting point A to the end point B, the robot moves along a straight line. That is, during the motion from the point A to the point B, the orientation angle theta k is constant, and the position coordinates of the center of the robot body x and y are changing. At the point B, the orientation angle theta k is changed, such that the orientation becomes the new orientation that will lead us to another point. Now, this is just a formal mathematical decomposition of the motion, since in practice the actual motion between the 2 points might not look like this. That is, this is an approximation of the motion that enables us to mathematically analyze the geometry and kinematics of motion. However, if the time interval h between the time instants k and k plus 1 is relatively small, this formal decomposition relatively accurately approximates the true motion, Also, it is very important to keep in mind that at the time instance k and k plus 1, the locations and orientations correspond to the real locations and real orientations of the robot. What happens in between the time instance k and the time instant k plus 1 cannot be exactly modeled unless a more complex mathematical model is used. To repeat, from the mathematical point of view, the motion is decomposed into series of straight line motions and orientation changes. Let us now illustrate this with the following example. Here is the example. The goal over here is to move the robot from the point A to the point C by visiting the intermediate point B. The first step, while we are still in the point A, is to adjust the orientation θ1 such that the robot can move along the straight line from the point A to the point B. Here's how we adjust the orientation. We adjust the orientation in the point A such that the robot will move along the straight line from the point A to the point B. So this is the first step. Adjust the orientation. In step number 2, we move from the point A to the point B along the straight line for the distance s1. Here's the graphical representation. In step number 3, we adjust the orientation of the robot for the angle of θ2 such that we can move along the straight line from the point B to the point C. And in the final step, that is in step number 4, we move along the straight line from the point B to the point C for the distance of s2. Next, by using this principle, we will develop the kinematics model of the robot that mathematically describes this motion. Here is the basic idea. From the discrete time instant k to the discrete time instant k plus 1, the robot travels from the start to the end position. During that time interval, the robot had traveled the distance of sk. Under the assumption that the orientation θk remains constant, from this geometry we can establish these two equations. Namely, xk plus 1 is actually xk plus this distance over here, and this distance is sk multiplying cosine θk. On the other hand, yk plus 1 is actually yk plus this distance over here. The distance is actually sk multiplying sine θk. These two equations describe the location of the robot at the time instant k plus 1 under the assumption that the robot was at the location xk and yk at the discrete time instant k, and that it had traveled the distance of sk between these two discrete time instants. Next, we need to incorporate the rotation. In the endpoint, that is over here, we perform the rotation for the angle of delta θk. The final orientation is equal to θ k plus 1, and θ k plus 1 is equal to θ k plus delta θ k. By combining translation and rotation, we obtain the final kinematics model of the mobile robot, and here it is. And this is precisely the kinematics model that is obtained by using the forward Euler discretization method. That is, we use two approaches to arrive at the same model. The second approach, based on this simple trigonometry and physical intuition, is more elegant. Next, we will give several important remarks about the derived model. Usually, the travel distance sk and the change of the angle delta θ k are directly or indirectly measured by using sensors such as wheel encoders, accelerometers, gyroscopes, compasses, etc. The process of obtaining these measurements is called odometry. Often in robotics literature, you will see that sk and delta θ k are used as known inputs. That is, although these quantities are actually measured outputs of the model, they are actually considered as the inputs. Don't be confused by this. These inputs are measured at the discrete time instant k plus 1, that is, after translation and rotation, and they are known. That is at the end of the movement. This means that the model can be written like this, where instead of delta, theta k, and sk, we write uk1 and uk2, where uk1 is sk and uk2 is delta theta k. Now, this represents a non-linear model. The states are xk, yk, and theta k. The inputs are actually obtained at the discrete time k plus 1. And generally speaking, this model is used to develop Kalman filters, SLAM algorithms, dead reckoning algorithms, etc. Okay, this would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.